Hello everyone, so we're going to get started on our part 2 of the nuclear chemistry notes. We're going to start off with something called energy levels, and these are a group of electrons with similar energy. So we're going to take a look at these different energy levels, but when we have electrons in the same energy level, that means they're going to have about the same amount of energy to each other. We represent what energy level they are in with this something called a principal quantum number, or a lowercase n. So instead of writing energy levels every time, we can say n equals 1, and that would tell us that our electron is in energy level 1. So this is the assigned energy level to a specific electron. So it can tell us, like from our POGL with the electrons and energy and light, it can tell us which electron we were in, or which energy level we were in. So we did do this in the POGL. We wrote n equals this or n equals that to tell us where those electrons are moving between. So generally speaking, electrons in lower energy levels are closer to the nucleus. So we have our nucleus here, and we can have energy levels like this surrounding the nucleus. So this energy level here is going to be closer to the nucleus than the one out here, okay? Which means then that those electrons that are in the first energy level are a lot closer to the electrons, or to the nucleus, than the electrons in that outer energy level. Energy of an electron is quantized, which means that the energy of an electron can only have specific values, but cannot have values in between. So we kind of went over this in the POGL, that we can't have an electron in between energy levels. They need to be going from energy level 1 to energy level 3, or energy level 6 to energy level 5. They can't be found in energy level 1.5. They need to be jumping between specific energy levels. They can jump between any energy levels, but they have to go from one to the other. They can't be found in between there. So let me have a little diagram to show us our energy levels. So I'm going to draw an arrow going this way, and this is going to indicate energy is increasing as we go up. So we have our nucleus down here, and then we're going to have energy level 1. Let's put it here. Energy level 2 is pretty far away from energy level 1. Energy level 3 is a little bit closer to energy level 2. Energy level 4 is even closer, and it continues to get closer and closer. And then we'd have 5. I'll kind of draw it out here. And then we can kind of have an infinite number, and they're just going to increasingly get closer and closer together. Okay, so we have energy level 2 and 1 are pretty far apart. And then as we go up, they get closer and closer together. Okay, and again, we have our nucleus down here. So energy level 1, you can clearly see, is a lot closer to the nucleus than something in an electron in energy level 5. This happens to be like a bookshelf where we can't find books in between shelves. Obviously, they have to be on one or the other. And it takes more energy to fill the top of a bookshelf than it is to the bottom. It's going to be the same thing with energy levels. It's going to take less energy to fill an energy level 1 with electrons than it is to fill energy level 5. And that's why I say over here, as we go up, there's increasing energy that it takes to go that far, because we're moving between more and more energy levels. However, unlike bookshelves, our first and second energy levels are very far apart. And then they get closer together as you get higher up. Get closer together as we get higher up. So we saw that our first and second one are really far apart, and then 4 and 5 are a lot closer together as we go up. Okay, so changes in energy levels. An electron can change from one energy level, I didn't leave enough room for that, sorry. From one energy level to a higher energy level, only if it absorbs the energy equal to the difference, a difference between the energy levels. So if it absorbs enough energy to move between energy level 1 and energy level 5, then it can move to a higher energy level. So we know it needs to absorb energy. Then we know to go to a lower energy level, we are going to release energy when we do that. Or emit, we've seen that word as well. Emit energy, and that's going to be in the form of light. So this stuff, kind of with energy levels, we've sort of gone over already from the POGIL. Now some new stuff is valence electrons and Lewis dot diagrams. So valence electrons are the outer shell electrons. And what I mean by this is if we have a picture of our atom, say we have 3 energy levels, it's going to be the electrons on this energy level. Those are the valence electrons, so on the outer energy level. They determine the chemical and physical properties of an element. So they tell us how this atom can or cannot bond, depending on how many valence electrons it has. And the goal of all of our atoms is to have 8 valence electrons, like our group 18 noble gases. So the goal of bonding, which we'll get into, is to have 8 valence electrons, like the noble gases in group 18. They have 8 valence electrons already, which is why they typically don't really bond. Okay, so that's valence electrons. We use those valence electrons in our Lewis dot diagrams. And some of you incorporated this into your element project. You guys drew the Lewis dot diagrams. So these use valence electrons to show paired and unpaired electrons and how an atom or ions can or already did bond with something else. Okay, and I say ion, so we know atoms are neutral, ions have charge. So if we have an ion, that means it's gains or loses electrons. And we're going to show that in our Lewis dot diagrams. When we have ions in their Lewis dot diagrams, we put these in brackets. Oops, them, not theme, them in brackets, and we have the charge on the outside. So we can show that that's an atom and not that's an ion and not an atom. Okay, rules for drawing diagrams are pretty simple, but first we're going to count the valence electrons because that's what we need to draw them. Second, we're going to draw the symbol of our atom that we're looking at, or ion, and then we're going to start at the top with only 1 electron and move around the symbol with 1 electron at a time. At the end, if there are leftover electrons, we can start to pair them up. Okay, and when we draw these, there's kind of 4 quadrants. There's the top, the right, the bottom, and the left. So if we have our symbol here, we have these kind of 4 quadrants. So we can have, so again, like I'm saying, let's say we have 8 valence electrons. We'd start up here, 1, 2, 3, 4. And then if we have 8, we can go back around 5, 6, 7, 8. So we can have a total of 4 pairs. So this would be a pair here, this would be a pair here, here, and here. We're not always going to have 8 valence electrons with our neutral atoms, but that's the point of them bonding so that they get 8 valence electrons and 4 pairs. So let's look at some elements here. So let's look at magnesium. Magnesium is in group 2, so it's going to have 2 valence electrons. So when we draw the dot diagram, we're going to start on top with 1 and then go around and add another one here. We are not going to draw this. No, that tells us that we have 2 paired electrons, and so it looks as if magnesium cannot bond to anything. Whereas the first one I drew shows us that magnesium has 2 unpaired electrons and can either give those away or bond to something. Let's look at carbon. Carbon's in group 14 and has 4 valence electrons. So we're going to draw a carbon symbol. We're going to start with 1, and then 2, 3, 4. So that's going to be the correct one. We are not going to draw it like this. Because again, that shows me that there are 2 pairs, and it doesn't clearly show where my unpaired electrons are. Then I mentioned something about ions. So let's look at bromine with a -1 charge. Bromine's in group 17, so it as an atom has 7 valence electrons. But this -1 charge here means we're adding 1. So now we have 8 valence electrons. So I'm going to draw bromine with its 7. So we have 1, 2, 3, 4, 5, 6, 7. So that shows me there's 1 unpaired electron. But now if we add 1 electron to it, now we get 1, 2, 3, 4, 5, 6, 7, 8. And we're going to put this in brackets to show that it's an ion and have our -1 charge on the outside. So we have neutral atoms and we have our ions that we can draw. And then it'd be the opposite for if we had something with a +1 charge. So I kind of briefly went over this and I said magnesium's in group 2, so it has 2 valence electrons. Carbon's in group 14, so it has 4 valence electrons. We can use our group numbers to figure out how many valence electrons each neutral atom has. Group 1 has 1 valence electron. Group 2 has 2. Group 13, we take that 3 out of there and we can say that group 13 has 3. Group 14 has 4. Group 15 has 5. Group 16 has 6. 17 has 7, and then 18 has 8, and that's why it typically doesn't bond. So this tells us the number of valence electrons in each group. And it's just an easy, quick way to figure those out just from our group numbers. Or we are going to learn about later in this second half of the unit about electron configurations, which you can also use to figure out the number of valence electrons. So that is Lewis dot structures, and I'm going to have you do some practice now with drawing these on a worksheet that I'll post on Classroom.